Welcome to Summarize Science, where we break down complex research into simple terms. Have you ever looked at an electricity bill, especially for a large business, and wondered why it's so high? A big part of that cost can come from something called peak demand, a charge for the single highest spike of energy used during the month. To fight this, many are turning to large batteries to shave these peaks by supplying power when demand is highest. But figuring out the best size for that battery and how to control it is a huge challenge. This paper, Robust Rule-Based Sizing and Control of Batteries for Peak Shaving Applications, tackles this exact problem. Traditionally, controlling these batteries involves complex methods like Model Predictive Control, or MPC, which tries to predict future energy usage. The problem is, these forecasts are often wrong, leading to systems that don't perform as well as promised. So, the researchers proposed something much simpler, a rule-based controller, or RBC. Think of it like a simple thermostat for the battery. If the building's power usage goes above a certain high threshold, the battery discharges to help out. If the power usage drops below a low threshold, the battery charges back up, ready for the next peak. But what makes this special isn't just the simple rule, but how they find the perfect thresholds. Instead of guessing, they use a process called stochastic tuning, using historical data to learn the optimal settings that would have saved the most money. They even created an adversarial version, which is specifically trained to be great at handling the worst-case, most extreme energy peaks. This makes the system more robust and reliable when it matters most. So, how did this simple, robust rule-based system stack up against the complex, forecast-based MPC? The results, shown in these graphs, are fascinating. When it came to the highest, most expensive peaks, the ones that really drive up the bills, the simple rule-based systems were, on average, more effective than the complex MPC. This chart shows the normalized daily peaks and lower is better. You can see the adversarial RBC often performs best on the highest quantiles. The study also looked at battery sizing. The old, optimistic methods often recommended oversized, expensive batteries. In contrast, the new method using simple rules suggested smaller, more appropriately sized systems. But perhaps the most important finding is about the financial promises. This chart shows the final levelized cost of energy, or LCOE, which is a measure of profitability. The researchers found that the financial estimates made using their RBC method were much closer to the actual, real-world results, while the complex MPC method often underdelivered on its initial promises of savings. So, let's recap the important points. The researchers developed a simple, rule-based controller for peak shaving batteries. By training this controller to be robust against the worst-case scenarios, it outperformed more complex, forecast-based methods at reducing the highest peaks. This approach also leads to more realistic battery sizing and more reliable financial predictions. What does this mean for the future? It means that deploying batteries to save on energy costs could become cheaper, more reliable, and less risky for businesses. This work shows that sometimes a simple, robust, and cleverly tuned rule can be more powerful than a complex prediction, paving the way for wider adoption of energy storage. Thanks for watching Summarize Science.